at Quantitative Investigations of Variation. This is for Year 12s and any Year 11s who are interested in A-level biology. So we're going to crack on. So how is variation measured? That's what we're focusing on today. You need your calculators today. We're doing some statistics, some stats. Nothing to be scared of. It's just literally plugging some numbers into a calculator. Now, recall quiz, high five. We don't want to forget those. So number one, what is the definition of a species? Number two, what is a gene? Number three, what is an allele? Number four, how does an immunological comparison work? That's a tricky one. That's what we looked at last lesson. And number five, what are the three types of averages? Which wasn't a question from previous, but you should know that from your GCSE maths. Press pause, have a go at those questions, and then when you finished, unpause, and we'll go through those. Right, so how is variation measured? Right, so definition of a species, a group of organisms with similar features. But the most important thing though is they can reproduce to produce live fertile offspring. What is a gene? A gene is a sequence of DNA that codes for a polypeptide, i.e. a protein. What is an allele? An allele is a different version of a particular gene. How does an immunological comparison work? That's the one where we talked about where you extract a serum from a human, you inject it into the rabbit makes antibodies for the human proteins, the human antibodies, and therefore when you inject that rabbit serum into other organisms, the degree of precipitation, when you compare it to the human precipitation, shows you how closely related they are. So the more precipitation, the more closely related to the original species that you used. So in this one we used human. Number five, what are the three types of averages? If you didn't know already, then you shouldn't be here because it's primary school maths. The three types of averages are mode, median, mean. Mode, median, mean. What's the difference? Well, mode is the most frequent. Median is always called the medium. So you go from smallest to highest, line them up, and you find the middle number. And the mean is you all add them all up together and divide it by the number of data. Okay, so what we're focusing then, what we're learning about investigative variation. Today we're learning to describe how variation is measured. That's great. Looking at how what sampling is and why it's used, and explain the causes of variation. So looking at DC, I'm going to give you go into some other stuff as well. So quick little pause. If we have a look at our two little diagrams here, can you identify the similarities and differences between these species? So press pause, make a quick list, and then we will unpause if you've done that. So obviously you got apples and pears. So what's the similarities? Well, they're both fruit, they both have seeds inside of them, they both got stalks. What else can you see? They're both green, they both got a waxy waterproof layer on the outside. Obviously the fruit, so they're full of sugar, and there's some similarities. What's some differences? Obviously the shape, the shade of green, you could be the texture, the taste. Obviously there's all sorts of differences. Why am I going on to this? Well, when we look at the ecosystem all around us, there is vast variation, and we need to take samples of a population so that we can monitor what's going on in the ecosystem. Now you will learn more about population sampling as part of your course, and you'll be doing them as required practicals, field work and so on. And so this sort of relates with that particular topic, so it links in with that. So what do I need to know? You need to describe how variation is measured, explain what sampling is and why it's used, and describe the types of variation and their causes, and explain what is meant by mean and the standard deviation. Okay, so got quite a lot to get through, so I'm going to whiz really fast through this because most of this is really straightforward sort of GCSE stuff. So variation then, so you don't obviously have to do this, but in your books write down all the ways you are both similar and different to others in the room. Okay, so obviously there's so many differences amongst us: skin color, eye color, ear shape, eye shape, nose shape, hair color, hair, you know, if it's straight or curly, and so on and so on. So there's so many different differences between us. Now we've got different types of variation. We've got intra-specific variation and inter-specific variation. So intra-specific variation is within, so within the same species there's variation. So amongst all of us, there is intra-specific variation, just like what we saw on the previous slide. But when you look at the variation between different species, that's inter-specific variation. Okay, so a tomato and a fish will have inter-specific variation because they're different species. So what we talked about this previously, what causes variation? Well, we know it's either environmental or genetic influences, or it's a mixture of both. Now, sampling then. So when we're looking at the population, we look at the ecosystem, we take a sample, because you're not going to count every single daisy on the field. It'll take you, you'll be there forever. Okay, I know you've got plenty of free time on your hands, but it'll be a laborious task. You'll be there forever. So what you do is you take samples. So you only count from a certain area in the ecosystem or in our area that we're looking at. And what we try to do is take a representative sample. So you can see those guys there taking quadrats there and counting within that square, that quadrat, and even under ocean quadrats. Okay, so consider how best to sample the area which represents an area under a log in order to find out how much each type of bug is present in the total area. Now you've got to think carefully about what you are trying to do without maybe thinking about it. Okay, so you're not going to just go around randomly chucking quadrats around. Okay, you need to think about what are you trying to get, what is the data, what data are you trying to represent. So we call that representative data. Okay, if I'm trying to count under a log, I'm not going to go into the ocean and start counting bugs in there, am I? Okay, or in the middle of a field where there's no logs. So you need to think of what is the question and what is it that I'm trying to investigate. But then you're going to have to really consider these things. The three key words you must know, or what you really need to consider: sampling bias, chance, and random sampling. Okay, and we need to, right, so what do I mean by bias? Now obviously if I go to a football match, now obviously you all know that I support the best team in the world. Obviously you know that's Aston Villa. But if I decided to go to a neutral ground, a neutral game, I'm a Villa fan, but I don't support Liverpool or Man United. I'd be a neutral. However, I probably got a more bias towards Liverpool, because Man United, as I was growing up, when I was a wee lad, they kept bleeding winning everything, every year, everything, all the time. A bit like Man City have been doing over the last few seasons, all right? And they really, and there's a song, if you hate Man U, stand up if you hate Man U. And you grow up doing that. So obviously I've got a negative bias towards Man United, only because I grew up in that era. Although Liverpool were winning things before Man United. But if I was at that game, I'd probably have a slight bias towards Liverpool. I'd have a soft spot for Liverpool, because I haven't won anything for ages. And they may never again after this lockdown, because they might scrap the season. Anyhow, I'm digressing. So sampling bias then, you can't think about, if you go into the field and count the daisies on the field outside Craythorne or behind Craythorne, I want to look at the field and count the number of daisies. I'm not going to look for the patches where daisies are and chuck my quadrat over there, because that will be sampling bias. If I'm looking for how many daisies on average on the field, I'm not going to go just to the area where there's daisies, because that's going to be sampling bias. The other thing is, if I'm looking in a particular area, I might by chance, by accident, only go to those areas where there is daisies. So that could happen. So you need to try to mitigate those things. We're trying to take out sampling bias by, you know, trying not to go towards where all the daisies are, and also trying to eliminate chance. So chance is this, that if you're looking at certain, you know, counting the height of, I don't know, the buttercups, and each buttercup is 5 millimeters high, but you want to count all of them, and take a representative sample. Now you're going to expect to get ones that 4, 5, 6, 7, 8, 4, 3, 2, whatever, right? But I might, by complete chance, by accident, gone to 5 different places, and they're all been exactly 5 millimeters or something like that. Okay, so there is chance, and you want to mitigate chance. So what you do to mitigate chance, what do you do to mitigate bias? You need to do something called random sampling. So random sampling reduces the idea of bias. So when you're trying to do these quadrats, you do a random number generator, you turn the area into a grid coordinates. Now you did this back at GCSE when you did your required practical with the quadrats. You made a grid area and you do random coordinates in that grid by a computer generator, and you put your quadrat in those places. Therefore it's completely random. If you don't want to do that way, which is the best way to do it, you could just chuck the quadrat behind your head, obviously in a sensible fashion, not to try to throw a boomerang and knock somebody out. So you just throw it behind you. But then again, there will be an element of bias, because you might see, oh, in the back of your eye, you can see some buttercups over there or daisies, and you go around chucking it over there. Okay, so you need to do it randomly by a number generator, a grid method, and to reduce the chance thing, you want to have a massive, large data sample, thereby reducing the probability that some of your data is by chance. Okay, and that all gets fed into your statistics. Okay, so you want a large data set to avoid any bias, to reduce chance, and therefore mitigate this, so your statistics is going to be more accurate. So we talked about causal variation is either genetic or environmental or a bit of both. Okay, so how would you come up with a reliable estimate for the number of daisies in this field? So you've done this in your required practical back in your old GCSE, and you're going to do exactly pretty much the same required practical for your A-level. Okay, so random number generator, grid coordinates, quadrats, massive sample, count the stuff in those quadrats, then you're going to need to average them out, okay, by doing a mean. So that's what you got up to at GCSE level. However, at A level, we're going to have to start analysing our data to a higher degree of accuracy, and looking at the probability that the results are not due to chance. Okay, so we'll start looking at that type of terminology. We'll look at statistics. So here's two sets of data. I've got blood groups, and I've got the height and the frequency of the number of people with those particular height. Now, if you were going to plot these two sets of data, how would you plot the blood group and how would you plot the height? Well, what you do with blood group, because you've got this discontinuous variation there, we've got data that is what we call categoric variables. They're categoric variables. They're just words or names of stuff. Okay, so you could do that as a bar chart, or you could do it as a pie chart. Now the obvious one, the most easiest one, is a bar chart. Whereas when you got continuous data like so, okay, and continuous data like this, you would plot them in a line graph, okay, or a scatter graph or a line graph, and you'll get what we call a normal distribution. Now this is where we're going to start looking at the types of variation. So the different types of variation, recognize them from data and understand their causes. What is a normal distribution? Now we talked about this already when we looked at the types of selection and how you get selection pressures. Okay, so we looked at stabilizing selection and disruptive selection, and we looked at the selection pressures where it moves across. Okay, so we looked at normal distribution before. It's that sort of bell-shaped curve, and we're going to calculate and interpret what standard deviation is. So this is your grade B and your grade A stuff. Okay, so your normal distribution, well, what do averages look like? Well, averages look like this. You've got your mean, your mode, and your median. Now, you could, if you look at your data, if you manipulate your data, your median might be in the middle somewhere, but the most frequent number might be the bigger number. So bigger numbers might be more frequent, but the middle number out of all of them could be lower down. So you could end up looking like this. Now, if you did a mean, it'd look like that. However, when we do a normal distribution, your mean, mode, and median are exactly at the same point. All of the numbers are in that middle bit there. Okay. Now, we come back to our blood group. Our blood group would have been like a bar chart, but our heights would have been, remember our polygenes, would have been a normal distribution like so. Now, what do I mean by standard deviation? Well, we know what the mean is. You add them all up and you divide it by the total numbers that you've got, and that gives you an average, okay, or a mean average. Now, what does the standard deviation mean? Standard deviation is telling you how spread your data is from that mean. Because remember, you've got lots and lots and lots of numbers, and the mean is the average, or the mean average is in the middle there. The most of them are here. But some of the numbers were higher, and some of the numbers were lower. But you're looking at the spread of the numbers away from that mean. So if your numbers are more closer to the mean, if you've got lots and lots of numbers, but they're all very, very close to the mean, you'd get a normal distribution that is very pointy like this, and then it'll widen out like that. Now, the closer you are to the mean, the more your data is closer to the mean, the smaller your standard deviation. The more spread out your data is, and that bell shape gets fatter and wider, the higher your standard deviation. Now, which is better, the smaller standard deviation or the higher for the accuracy of your data? Well, it is to do with that. There you go. The accuracy is basically how true are your results. How accurate means how true are your results to the real value, the true value. The closer you are to the mean, the more accurate it's going to be. So the smaller your standard deviation, the better. The larger the standard deviation, not so good, because the bigger the standard deviation, it tells you that the data is more spread out. But what is the standard deviation? It's the point at what we call inflection. The point of inflection. It's where this curve starts to curve out. So the bit at the beginning is what we call a convex shape. It's curving sort of outward like a convex shape. And the bit where it starts to concave, go inwards, that's the point of inflection. And the distance from the mean to the point of inflection where it starts to become concave is your first point of standard deviation. So your first standard deviation, 68% of your data is within the first standard deviation. Okay? And then nearly 2, says 1.96 then, but nearly 2 standard deviations is where if you carry on that line, it's now there. Then it starts to curve out again. That is your second, nearly your 1.96 standard deviation, but let's just round it to 2. That's your 2 standard deviations, okay? Now 95% of my data, all of my data is within 2 standard deviations, which means 2.5% of the data is on this side and 2.5% of the data is on that side, because those two must add up to 5%, okay? So that's what standard deviation is all about. All you need to be able to do is stick it into a formula, calculate it, see what that number is, and that's going to be your standard deviation. Now, the bigger the standard deviation, the more inaccurate, or the bigger the spread of the data is from the mean. You want the data to be as close to the mean as possible, because every single piece of data is closer to that true value. Okay, so the mean then. The mean, this is the maximum height of the curve and gives us the average value, but tells nothing about the range. It just tells us the average, not or the mean. It doesn't tell us how widespread it is. So this is why we have the standard deviation. The standard deviation is a measure of the width of the curve and gives an indication of the range of values either side of the mean. So how spread it is from the mean. Distance from the mean to where the curve changes shape, that inflection point from a convex to a concave. Now from this data, from this graph, you can see 68% of the values lie within the first or one standard deviation. So that first one, these lines here, the 68%, one standard deviation means this little arrow here. That second arrow there is telling you 95% of the data is 1.96, nearly 2 standard deviations away from the mean. So you can do this from your from the PowerPoint, and you can have a go at those questions. But here's a worked example of how you calculate a standard deviation. So find the standard deviation from these numbers. Now what do I actually do? How do I do this? Here is my data. I went onto the field and I counted these numbers: 4, 9, 11, 12, 17, 5, 8, 12 and 14. You can see I can count. So those are a set of numbers. Okay, what do I do to those numbers? Well, first thing I need to do is work out the mean for those numbers. I add them together and divide it by 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 numbers. So add them together, divided by 9, gives me 10.222. Okay, so that's the mean. Now, what do I do with that mean? Now this little equation is my standard deviation equation. It's the square root of, now this little E shape is what we call sigma. Now it's a Greek letter. All it means is the sum of. It means add them all up. Now what do? I need to get my individual data and I need to take it away from the mean. So I need to go 4 for my individual data, take it away from my mean, which is 10.22. Okay, that's going to give me a negative number. But I don't want negative numbers. So I need to square it. So then you square it. Okay, so I do 4 take away 10.22 whatever, so that's what, -6 or something like that. And then I need to square it. Then I square it. So if it's -6 squared, it'll be 36. Now obviously this number is a bit more than that, right? So therefore, look, there's the answer, 38.7. So you do that to all of the numbers. So I do it to 4, I do 4 take away that, square it, 9 take away that, square it, 11 take away that, square it, and there is my set of numbers. You can see there's a lot of calculations to do, right? So I've got all of my these individual data, take away the mean, and I've squared them, and then I get all of these numbers and I need to add them all up. So if I add them all up, it gives me that 139.55. So just try it out, okay? I might have made a mistake, I sometimes do. So add them all up, you should get 139.55. Now what do? I divide this number, number 4, I divide this number by n-1. So n-1 is the number of data sets, which is 9. I take away 1, which equals 8. So I do 139.55 divided by 8 gives me, into your calculator, 17.44. So all of this answer here is 17.44. But to finish it all off, I need to square root that answer and I get 4.18. And that is my standard deviation. That's my answer. Okay, so that's the end of this lesson. If you got any questions or if I've made a mistake and you want to correct me or ask me any questions, please go to the Show My Homework and you can ask me questions via there, or you can leave a comment in the YouTube of My Smart Learning, okay, if you've subscribed. So thanks for watching. That is the end of all of the Year 12 work now. So that's the end of Chapter 10. If you've got any questions, please get back to me. If you've learned something, that's great. I really appreciate you guys watching and keeping up with me all this time. I'm going to go on to photosynthesis, which is Chapter 11, which is officially the beginning of Year 13 work, because it's the A2 work, where the old scheme would have been A2 work. You just finished all the AS content. Please keep watching the videos, liking the videos, subscribing and sharing. And I forgot to give you your virtual high five. How could I forget? I know you've been asking for it all this lesson. It's been, it's been itching you. So if you got all 5 right, it's a great virtual high five from me. Take care and I'll see you next time. Virtual high five.